Isn't it a new pavement? Why are cracks already starting to show?
It happens all the time.
So you're telling me that this is actually normal?
Pretty much. I mean, shocking, isn't it? It's called early age cracking. Concrete is the most widely used building material today. It's everywhere. From construction roads, bridges, houses, and water resource facilities, concrete continues to become a significant contributor to the progress of the society. But there is one major problem: concrete cracks. Concrete cracking is a generally accepted notion by engineers. One of those types of cracks is called early age cracking. By definition, these are cracks that appear within the first 7 days after placement of the concrete. Although the early age cracking itself does not affect the overall strength of the structure, it is quite an alarming sight for ordinary people. Looking at these long-term effects, untreated cracks may cause such problems such as an ingress of aggressive agents, which will eventually put the structure's strength at stake.
One of its main causes is thermal stress. Early age cracking occurs due to temperature differences and stress development during the hardening of concrete. This is caused by the high generation of heat when water reacts with cement. This is known as the heat of hydration. States that only 20% of cracks are caused by non-thermal factors. ACITU in 2018 recommended to use type 4 cement due to its low hydration heat property. However, this type of cement is costly. Being uneconomical, it makes it extremely difficult for engineers to apply it in construction.
Another study has shown the potential of copper tailings to reduce heat of hydration in early age cement. What are copper tailings, you ask? These are finely ground waste after copper mineral has been extracted from the ores during beneficiation. The disposal of mine waste is one of the major global environmental issues. Copper mines usually have a dumping facility in form of a dam or a pond. This type of dumping also causes problems in terms of land provision, since these dumping sites take up a large amount of space. Moreover, the failure to provide an enclosed dumping sites can bring huge aquatic problems, since copper tailings exposed to water can produce sulfuric acid and other harmful substances such as lead, arsenic, and mercury.
Going back to the problem of early age cracking, our team will propose the incorporation of copper tailings into the concrete mixtures in order to lower the heat of hydration. By doing so, we'll not only do that, but it will also address the environmental problem of disposing these materials by putting them into good use. Studies have also shown that the incorporation of copper tailings will contribute to a higher compressive strength. Most importantly, this proposal, being low cost, may be easily applied in construction, especially in its economic aspect.
To further achieve the goal of low hydration heat, our team proposes the incorporation of copper tailings to blended cement. Blended cement, or type 1P cement. Type 1P has a slow hydration process and thus generates less heat than OC. Furthermore, pozzolana consists of silica material which makes it cheap and hence reduces the cost of the cement, making it economical to use.
Our proposal in conducting this experimental research on incorporating copper tailings and type 1P cement would require an endorsement from an ACI committee. With this, our team believes that the ACI Committee 209, creep and shrinkage in concrete, would be the most ideal avenue to realize this proposal.
The proposed mixture designs will be anchored to studies supporting the characteristics of copper tailings in potentially replacing cement and decreasing its heat of hydration,
which shall be standardized in accordance with specific ACI and ASTM guidelines. These will serve as the determining factors to attain significant desired results, most suitable for the production of a normal strength blended concrete that is of high performance and quality, and at the same time sustainable. Specifically, 4 setups will be employed, which shall be tested accordingly to measure optimum capacity of each design. In formulating the proposed mix designs, proportioning by weight method will be used. The mixture design setups will be composed with variation in the composition of the aggregate binder, where extracted copper tailing powders is to be added with varying proportions. Selection of the cement type and source is in accordance with ASTM C917 or standard test method for evaluation of variability of cement from a single source based on strength. Type 1P cement based on the optimal content will be used. Further, proportioning of components other than aggregate binder will be in accordance to ACI 211.1-91 or the standard practice for selecting proportions for normal, heavyweight, and mass concrete. As one might expect, a slump test following ASTM C143 and a water absorption test following ASTM C1585-13 will be conducted in the preparation of the material. In order to measure the sample's heat of hydration, procedures in ASTM C1753 or C1753M-21A will be followed. Samples for early age deformation will also be prepared following the ASTM C31 guidelines. Rectangular samples of the said proposed mixture designs will be prepared and stored 12 hours before the initial measurement. Its initial and final length will be measured 7 days apart. Although the concrete technology has been advancing for the past 3 decades, there is still no permanent solution to early age cracking. Presenting a solution that is both environmental and economically friendly is important as it puts action into practice. Our team proposes to present a solution to one of the leading causes of early age cracking, which is thermal stress, while considering the cost and the environment. Relax, we'll stop the cracks.